Welcome to the deep dive. We're jumping straight in today, looking at something truly intense, an all-engine flameout in flight.
Yeah, it's about as critical as it gets in aviation.
It really is. You're not just dealing with a technical problem. You're suddenly in a race against gravity, against time, and your only tools are the procedures in the Quick Reference Handbook, the QRH.
And the clock is ticking loudly. It's the ultimate test, really, because when you lose all engines, you're essentially a glider, a very heavy one, and altitude is everything.
Exactly.
Our sources today really emphasize that getting the relight sequence wrong isn't just about delay. It basically guarantees failure, or at least a much harder time getting those engines back. We're talking seconds making the difference between a successful restart and losing thousands of feet you desperately need.
So today our mission is to unpack a specific event, an A320 flight, where this nightmare scenario became reality.
A real-world case study.
We'll look at what the crew did, what went wrong during those incredibly stressful minutes trying to restart the engines, and crucially how this one event led to changes across almost the entire Airbus fleet, A320s, A330s, right up to the A380.
Yeah, the ripple effects were huge.
We're really going to dig into why one seemingly small detail, like where the thrust levers are set, can make or break an emergency restart. Okay, let's set the scene. We have an A320, CFM 565B engines. It's late evening. The flight's already had a tough time diverted because of bad weather.
Right. They had a 3-hour stopover at the diversion airport. Then they took off again around 9:51 p.m. local time, trying to get to their original destination. So it's dark, weather's still a factor.
They're climbing out, initially cruising at flight level 240, that's 24,000 feet.
Yeah.
Everything's normal, autopilot engaged, auto thrust on.
Standard stuff.
Yeah.
But they see trouble brewing on the weather radar. Storm cells. So they ask ATC for a deviation northward to try and avoid the worst of it.
And they make a pretty significant turn, right? A 90-degree left turn.
Yeah, sharp turn towards their destination, trying to skirt around this weather system.
And it's just after that turn
that
everything goes wrong. Not gradually, but bam.
Instantly. And violently. The aircraft flows right into severe turbulence, and this is key, a hailstorm. A really intense one.
So not just bumps, actual impact.
Oh, yeah. The crew reported hearing loud bangs impacts on the airframe, and they could see damage immediately. Both windshields, left and right, were hit. This was serious physical assault on the aircraft.
And at the same time, the systems just collapsed.
Pretty much. The ECAM, the electronic monitoring system, just lit up. Alerts for everything, anti-ice faults for the windshields, ENG1 stall, ME-2 fault, a whole cascade.
And the most critical failure.
Both engines flamed out simultaneously. Total loss of thrust.
Wow.
And then almost immediately, as the autopilot and auto thrust clicked off, the cockpit went dark.
Dark, like completely dark.
Pitch black, apparently within a second. The aircraft dumped into its emergency electrical configuration, EMIR ELEC. So the essential flight instruments stayed on, powered by batteries, but everything else gone.
That's terrifying. Just imagine severe turbulence, hail hammering the plane, no engines, and suddenly you can barely see your instruments.
And here's something chilling from the data. For the next 2 minutes and 46 seconds, nearly 3 minutes, the flight recorders didn't capture anything. There's a gap.
3 minutes of nothing while they're falling.
Exactly. Think about it. They're trying to figure out this catastrophic failure, battling turbulence, physical damage. The engine silence must have been deafening, unreliable speed readings, and basically flying by the dim emergency lights. We don't have a detailed record of exactly what they did in those first critical minutes.
The pressure must have been unbelievable. So how did they get power back?
They managed to get the auxiliary power unit, the APU, started. That's the small engine usually used on the ground. Once the APU came online, it restored electrical power to the main systems.
Okay, so lights back on, screens back up. What was the situation then when the data comes back online?
It was grim. Both engines confirmed out. Airspeed indications unreliable. We'll get into why later. And the flight control law had switched from normal to alternate.
And they'd lost altitude.
A significant amount. They were down to 18,100 feet. That's a loss of 5,900 feet already.
You mentioned alternate law. Can you just quickly explain what that means for the pilots in this situation? Why is that significant?
Sure. In normal law, an Airbus has huge protections. It physically won't let the pilot stall the plane or overbank it or overstress it. It keeps them inside a safe flight envelope.
Okay.
Alternate law. While most of those protections are gone, the plane responds much more directly to the side stick, kind of like a more conventional aircraft, but you lose that safety net. The pilots can stall it, they can overstress it, And dealing with that, plus unreliable airspeed, plus severe weather, it's incredibly demanding.
So fewer safety nets, damaged plane, no engines. But they were trying to fly the correct emergency profile.
Yes, the data shows they were. Their pitch attitude was recorded at minus 3.5 degrees. That's pretty much exactly what the QRH checklist calls for to maintain the optimum speed for a windmill relight using the airflow to restart the engines.
So they were handling the aircraft itself quite well, considering.
They were. Even with the speed showing an unreliable 232 knots, they were flying the descent profile correctly. Excellent airmanship under the circumstances.
But there's always a but, isn't there? A crucial procedural detail was missed.
A critical one. During this whole period, right from the flameout, the thrust levers were pushed forward to the TOGA position takeoff go around thrust.
And they stayed there.
They stayed there. And that single mistake, keeping the levers in TOGA instead of pulling them back to IDLE as the procedure demands, well, it basically sabotaged every restart attempt they made for the next 8 minutes.
8 minutes, wow. Flying the plane right, but missing that one lever movement.
It shows how vital procedural discipline is, even or especially under extreme stress.
So before we get into the attempts themselves, let's just quickly touch on why those engines flamed out in the first place. Because the weather they flew into, it was off the charts.
We're not just talking about a bit of hail then.
No, not even close. The post-incident analysis found that the intensity of the hailstorm, the amount of water and ice ingested by the engines, it actually exceeded the design and certification limits of those CFM56 engines.
By how much?
By about double. The concentration of water and ice was roughly twice what the engines are certified to handle, so they essentially choked. The hail likely caused internal damage too, contributing to the immediate simultaneous flameout. It was an extreme environmental event.
Okay, that explains the engines. Now let's circle back to the unreliable airspeed and that alternate law. What caused that?
That was down to physical damage at the front of the aircraft. The hail had battered the radome, that's a fiberglass nose cone covering the weather radar.
When the radome gets damaged or destroyed, the airflow over the nose becomes turbulent and messy. That messed up airflow goes right over the air data probes, the sensors that measure air pressure to calculate airspeed.
Ah, so bad airflow means bad data.
Exactly. The probes gave unreliable readings, the flight computers recognized the sensor data was garbage, and that triggered the downgrade from normal to alternate law. Physical impact causing system degradation.
Okay, so they're battling the elements, a damaged plane, and system issues. Now let's look at those 7 failed relight attempts. What went wrong procedurally?
Well, the first and most persistent error was the thrust levers, still stuck in TOGA.
Right, and the QRH, the checklist, specifically says,
set thrust levers to IDLE. Before you attempt the relight, it's step 1.
Why is IDLE so critical? What happens if you try to relight in TOGA?
It's about stability and energy management. When an engine relights, you want it to catch and stabilize at a low power setting, at idle. If the levers are in TOGA, the engine's computer, the FADEC, immediately tries to spool it up to maximum thrust as soon as there's combustion.
And that's bad because
2 major risks. 1, you can get an engine stall. The compressor can't handle the sudden demand for air matched with the fuel being dumped in. 2, you risk an EGT overlimit.
EGT, exhaust gas temperature.
Precisely. It's the temperature limit for the hottest part of the engine, the turbine. If you get a sudden, uncontrolled surge of fuel and thrust on startup, a hot start, the temperature can spike way above the limit.
Damaging the engine permanently.
Yep. Exceeding the EGT limit can cook the turbine blades, basically rendering the engine useless, even if it momentarily relit. So leaving the levers in TOGA meant they were risking either an immediate flame out again due to stall, or damaging the engine beyond use if it did catch.
So flying the glide path perfectly, but setting themselves up for failure on the restart. That's tough. And the mistakes didn't end there, did they? The APU bleed air was another issue.
That was the second major procedural violation. After the initial attempts failed, they correctly turned the APU bleed switch on, using the APU to provide air for the engine starter motor, but then they tried to start both engines at the same time by turning both E and G master switches on simultaneously.
Trying to use the APU's air to spin up both starters at once.
Exactly. And on this type of aircraft, the A320, the APU simply doesn't have enough puff for that. Think of it like trying to inflate 2 massive truck tires at the same time with a bicycle pump. The APU can supply enough bleed air pressure to turn 1 engine starter effectively, not 2. By trying both, they split the available pressure, and neither engine starter got enough torque or speed to reach the necessary RPM for a successful start.
Oh, it's a hard technical limit they missed?
Under extreme stress, yes. It's a fundamental limitation of the system design for that aircraft size.
And I know you mentioned the A380 is different.
Right. The A380 is so much larger, its APU is much more powerful, designed to handle bigger demands. So its specific procedure does allow for attempting to start two engines simultaneously using APU bleed. But for the A320, A330, A340, A350 families, it's strictly one at a time.
Okay, so wrong thrust lever position, trying to start both engines at once. And there was a third key error, wasn't there? Something about ventilation.
Yes, and this is crucial. The analysis showed they performed no 30-second ventilation period between any of the failed attempts.
What does that mean, ventilation period?
The QRH procedure explicitly requires that after a failed start attempt, you must turn the engine master switch O off F and wait for 30 seconds before trying again.
Why? What does that 30 seconds achieve?
It clears out unburnt fuel. When a start fails or an engine flames out, there can be residual fuel vapor left in the combustion chamber and hot sections. If you just immediately try again, throwing in more fuel and ignition, you risk a nasty hot start, that EGT overlimit we talked about, or even potentially a tailpipe fire. The 30-second pause allows the airflow, even the windmilling airflow, to blow out that residual fuel, ensuring the next attempt starts with a clean slate, reducing the risk of damage or another immediate failure.
And they skip this every time.
The data suggests they were cycling the master switches quite rapidly, sometimes just seconds between attempts. No 30-second wait.
So to recap the errors. Levers in TOGA, attempting simultaneous starts on APU bleed and skipping the vital 30-second ventilation pause. That's a lot to get wrong under pressure.
It is, and it explains why they struggled for so long.
So after about 7 or 8 minutes of this descending rapidly, what finally worked? How did they get an engine back?
They eventually self-corrected, which is remarkable under that pressure. They made two critical changes. First, they finally pulled the thrust levers back to IDLE.
Okay.
Second, they set both engine master switches to OFF briefly, likely providing some ventilation, even if unintentionally timed. Then, crucially, they attempted to start only engine 1, leaving the engine 2 master switch OFF.
Focusing the APU bleed on just one engine.
Exactly. With the levers at IDLE and all the APU's bleed air pressure directed solely to the engine 1 starter, it finally caught and stabilized.
Success. How long it had taken and how much altitude was gone by then?
Engine 1 became available 8 minutes and 26 seconds after the initial double flameout. By that point, they were down to 9,100 feet.
Wow. They had lost 14,900 feet, nearly 15,000 feet, almost 3 miles vertically.
A huge amount of altitude burned through during those failed attempts. That successful start, done correctly, was the turning point.
Did they try to get engine 2 back after that?
They did. They made 2 more attempts to relight engine 2 using the proper procedure, but both failed. And later inspections confirmed why engine 2 had sustained too much internal damage from the hail. It was never going to relight in the air.
So they landed safely on just engine 1?
Yes. They managed a single-engine landing, still in alternate law, still with unreliable airspeed and those damaged windshields and redome. A testament to their handling skills in the end. But the sources are clear. The sheer duration of the emergency, the altitude lost, it was directly linked to the initial procedural errors during the relight sequence.
Okay, that case study is incredibly sobering. It really highlights the gap between knowing a procedure on paper and executing it perfectly when, everything is going wrong. Let's pivot now and really break down the correct procedures from the QRH. Why each step is there.
Absolutely. Understanding the why is key. And the first thing to grasp is that the procedure fundamentally changes based on your altitude.
Because altitude affects airflow.
Exactly. Air density, primarily. So, we have 2 main methods. Windmill relight, which works best higher up, and starter-assisted relight, which you need when you're lower down. ###A, windmill relight, higher altitudes.
Right, let's start with the windmill relight. This is the preferred option if you're still high, say, above flight level 200.
Generally, yes. The principle is simple. At higher altitudes and speeds, the sheer force of the air rushing through the dead engine is enough to physically spin the compressor blades to windmill them.
Like a propeller.
Sort of, yeah.
Right.
It spins the core up towards the minimum speed needed for compression and ignition. And a key advantage here, because you're not relying on the limited power of the APU starter, is that you can attempt to relight both engines simultaneously.
Okay, so what's step 1 in the QRH for a windmill attempt?
Maintain optimum relight speed. This is critical. There's a specific speed range listed in the QRH and often shown on the flight display where the windmilling effect is strongest.
Like the 9 at a 3.5-degree pitch the crew in the case study used.
Exactly. They flew that part correctly. You adjust your pitch to nail that speed. Too slow, the core doesn't spin fast enough. Too fast, you might risk other issues like compressor stall, depending on the engine. It's about maximizing that natural rotation from the airflow.
Got it. Speed first. Then comes the step missed in the case study.
Thrust levers to ideal. Absolutely non-negotiable. Pull them back before you introduce fuel and ignition.
And just to hammer it home again, why ideally?
Because you want a gentle, controlled start. IDEL tells the engine's fuel control system to only provide the minimum fuel needed to sustain combustion at low RPM. It prevents that sudden surge you get with TOGA, minimizing the risk of EGT over-limit cooking the engine or the engine stalling itself because it can't handle the sudden acceleration demand. Stabilize first, then accelerate.
Okay, speed set, levers at ideally. Next.
Set the ENG mode selector to IGN. This basically turns on the igniters in the combustion chamber, ready for fuel.
Makes sense. And then we hit that ventilation pause.
The big one. All ENG master switches to OFF for 30 seconds. Even in a windmill scenario, even trying both engines, this pause is mandatory before the first attempt and between subsequent failed attempts.
Let's really unpack the why again. We know it clears fuel, but paint a picture of what happens if you skip it.
Imagine residual fuel vapor hanging around in the hot engine core after the flameout. You hit the master switch on again immediately, fuel sprays in, igniters spark, that residual vapor flashes instantly, you get a rapid, uncontrolled temperature spike, the hot start. Best case, it just stalls again. Worst case, you exceed EGT limits, damage the turbine, or if there's enough pooled fuel, you could even get flames shooting out the back of tailpipe fire.
Not ideal.
Definitely not. That 30 seconds is the engineered safety margin. It uses the windmilling airflow itself to physically purge the engine, ensuring a clean, safe environment for the next ignition attempt. It protects the hardware.
Okay, 30 seconds of ventilation is done. Now what?
Now you can attempt the start. For windmill, you set all ENG master switches to on-N. Since you're using airflow, not EPU starter limits, you can try both simultaneously.
And then you watch closely.
You monitor parameters. EGT and N2, or N3 on Rolls-Royce engines. N2 and N3 are just measures of how fast the engine's core components, the spools, are spinning, shown as a percentage.
So you're looking for...
They're looking for N2 and N3 to start rising steadily, showing the engine is accelerating, and for EGT to rise, showing combustion, but crucially, staying well below the red line limit. A successful windmill relight might take a bit longer to stabilize than a starter assist, sometimes up to 2 minutes.
And if nothing happens after, say, 30 seconds of monitoring?
If there's no sign of light up, no rise in N2 and N3 or EGT, then the attempt has failed. You must go back. Both master switches OFF. Wait another mandatory 30 seconds for ventilation, and then you can try again. Or, if you're getting lower, you might decide to continue descending towards the altitude where a starter-assisted relight becomes possible, typically below FL200, hashtag maybe starter-assisted relight below FL200. Right, so as you descend, the air gets denser, but your speed might decrease, and eventually the windmill effect just isn't strong enough anymore. Usually below about flight level 200, you need mechanical help.
Enter the APU.
Exactly. If the APU is running and you typically start it as part of the initial emergency actions, assuming you're within its operating altitude limits, you can use its bleed air to power the engine's starter motor.
This is where the crew in the case study ran into trouble with the simultaneous attempts.
Precisely. Because the APU bleed air supply is finite, this leads to the most critical limitation of the starter-assisted procedure on most Airbus types. Only one engine can be restarted at a time.
Except the A380.
Except the A380, due to its much larger APU. But for the A320, 330, 340, 350, you must attempt them sequentially. Trying both at once starves both starters of the air pressure they need.
Okay, so you're below FL200, APU is running. Thrust levers should already be at IDLE from the windmill attempts, mode selector on IGN. What's the first step?
Still ventilation. ENG master switches to OFF for 30 seconds if you haven't just completed a failed windmill attempt and paused. You always need that clear out before introducing fuel and ignition via the starter.
Then there's a speed adjustment, isn't there?
Yes, an important one for managing the descent. The procedure calls to reduce speed to green dot speed.
Green dot, what's that signify?
Green dot speed is basically the aircraft's best lift-to-drag ratio speed for its current weight and configuration. Flying at green dot minimizes your rate of descent. You're gliding more efficiently.
So it buys you time.
Exactly. While you're trying to get an engine started, slowing to green dot stretches out your glide, giving you more seconds, more altitude, more chances to get the precision right. It's a trade-off, speed for time.
Okay, speed managed for best glide. Next step.
Activate the power source for the starter. APU bleed on. Ensure the valve is open, supplying air from the APU to the engine bleed manifold.
And then the crucial single engine step.
The defining action. Only one ENG master switched on. You pick an engine, maybe the one you think is less damaged, or just start with engine 1 and turn only its master switch on.
Why is this so effective compared to windmilling?
Because now all the APU's bleed air pressure is driving one starter motor. That motor spins the engine core much faster and more forcefully than windmilling alone could at these lower altitudes. It rapidly gets the engine up to the required speed for efficient compression and ignition. It's a much more positive starting action.
Monitoring period is the same. 30 seconds?
Yes. Monitor EGT and N2, N3 for 30 seconds. Look for the same signs. Rising core speed, controlled EGT rise.
And if that first engine fails to start within 30 seconds?
Master switch for that engine goes O off F. Now you have two choices for your next move. Option 1. You can make an immediate relight attempt of the other engine. So if you tried engine 1 and it failed, you can immediately turn the engine 2 master switch on in.
Why immediately? Doesn't the other engine need ventilation?
Because while engine 1 was attempting its start with its master on in, engine 2 had its master switch off F. Air was still flowing through engine 2 the whole time, naturally ventilating it, so it's considered ready for an immediate attempt.
Ah, clever. So attempt ENG1 fails master 1 off F, immediately master 2 ON.
Correct. That's option 1. Option 2 is if you want to try the same engine again, maybe you think engine 2 is definitely damaged, like in our case study, and engine 1 is your only hope. If you want to reattempt engine 1 after it just failed,
you need to wait.
You must wait. Master switch 1 stays off F for a full 30 seconds to ventilate engine 1 before you turn master 1 on in again for the second attempt. That mandatory pause comes back into play.
That procedural logic is so specific. You can see how in the heat of the moment, maybe descending through 10,000 feet, making those distinctions correctly, it's incredibly demanding.
It absolutely is. And it underscores why the initial errors in the case study 2 DJ levers, simultaneous starts, no ventilation, were so detrimental. They violated the fundamental physics and the safety logic built into the procedure.
The impact of that A320 incident clearly went way beyond just that one crew, that one flight. It served as a huge wake-up call, didn't it? Leading to industry-wide changes.
A major catalyst, yes. Airbus took the lessons learned very seriously. They recognized that maybe the procedures, especially around the starter-assisted relight and the ventilation, weren't as clear or easily interpreted under extreme stress as they needed to be.
So they rewrote the manuals.
Essentially, yes. A significant effort was launched to improve the operational documentation, the QRH, the FCOM, the big operating manual, and even the ECAM checklist displays on the screens to prevent misinterpretation. The goal was absolute clarity, particularly on that one engine at a time rule for starter assists and the critical 30-second ventilation.
And this wasn't just for the A320.
No, across the board. The scale of this update is pretty vast. We're seeing the revised all ENG fail procedures rolling out progressively.
Do we have a timeline for that?
Yeah, it shows the scope. The A320 family, A330, and A340 fleets are getting their updates around November 2024. The older generation jets, A300, A300-600, A310 are scheduled for March 2025. Then the A350, that's mid-2025. And the A380 updates are planned for 2026.
Wow, that's a multi-year rollout across the entire active Airbus fleet worldwide.
It's a huge undertaking. Training materials, regulatory approvals, software updates for ECAM where applicable. It shows how seriously they took the potential for confusion highlighted by this event.
And it's not just about clearer paper or digital paper. They're looking at smarter systems too, right?
Yeah.
Especially in the newer planes.
That's right. For the A350 and A380, which have more advanced system architectures, Airbus is actively studying how to improve the ECAM procedure itself through updates to the Flight Warning System, FWS.
What would that look like?
Well, the idea is to make the system more interactive, more context-aware. Imagine if the ECAM could detect that you're trying a starter assist with levers in TOGA, or if it senses both master switches on and when only one should be. The FWS might then provide a more specific dynamic warning or guidance message right on the screen.
Using the automation to catch human errors in real time during the emergency.
Basically, yeah. It's about leveraging the aircraft's own intelligence to help the crew adhere to the procedure correctly, especially when cognitive load is maxed out. It's an engineering approach to mitigating human factors risk.
Okay, so if we boil everything we've discussed down, all the case study details, the procedural deep dive, what are the absolute key takeaways for anyone listening?
I think there are a few core things. First, a successful engine relight in these conditions hinges entirely on following the procedure meticulously. There's no room for shortcuts or guessing.
Precision is paramount.
Absolutely. Second, that 30-second ventilation pause is not optional. It's the crucial safety step to prevent fuel pooling, hot starts, and engine damage. Skipping it dramatically increases the risk of failure.
Got it. Ventilation is key.
Third, understand the difference between the two methods. Windmill relights, done higher up, rely on airflow and do allow simultaneous attempts.
Right.
But starter-assisted relights below FL200 using the APU are strictly one engine at a time for most types due to APU bleed limitations. That distinction is critical.
Right.
And finally, the case study just hammers home how vital it is to maintain situational awareness and disciplined adherence to the QRH, even when everything is falling apart around you. Training and understanding the why behind the steps are essential for performing correctly under that immense pressure.
This has been fascinating, really getting into the weeds of such a critical procedure.
Yeah.
We've covered the physics, the stark difference between windmill and starter assist, and why that 30-second pause is so vital.
It's complex stuff, and the case study really brings the challenges to life. It showed us that even a competent, experienced crew who were flying the aircraft itself remarkably well under the circumstances.
Yeah, holding that glide angle.
They still made repeated procedural errors. The tow GA levers, the simultaneous starts, skipping ventilation that cost them nearly 15,000 feet and 8 minutes of precious time.
Which leads us to a final, maybe slightly uncomfortable thought for everyone listening.
Yeah.
If an experienced crew can struggle with that level of procedural precision, consciously waiting 30 full seconds while descending rapidly towards terrain feels incredibly difficult. What level of perfection can we reasonably expect from humans in such extreme duress?
That's the million-dollar question, isn't it?
And following on from that, how much responsibility falls on system design like those flight warning system upgrades being studied to act as a safety net, to actively minimize the chances for human error when the stakes are literally life and death?
It's that constant balance, isn't it, between human skill, training, discipline, and how much we can or should rely on automation to guide us or even save us from ourselves in those critical moments. That tension will absolutely shape the future of aviation safety.
A profound point to consider. Thank you for joining us on the deep dive. We hope this look into the intricacies of emergency procedures gives you a new appreciation for the systems and the human factors involved in keeping air travel safe. We'll see you next time.